Today I shall examine the variety of factors that determine the adsorption selectivity of a variety of mixtures in various microporous crystalline materials. To begin with, let's develop an understanding of the adsorption selectivity for a mixture that behaves ideally and the ideal adsorbed solution theory applies. Here are the tenets that must be obeyed for the IAST to hold. All the adsorption sites within the microporous material are equally accessible to each of the guest molecules. This implies a homogeneous distribution of gas adsorbates within the pore landscape. This also implies no segregation or congregation of guest adsorbates or preferential siting of one or more of the guests within the pore landscape. Furthermore, the IAST demands that there is no change in the specific surface area of each molecule. This implies that the surface area occupied by any molecule is the same whether it is adsorbed on its own or in the presence of partner species. This implies no molecular clustering due to, say, hydrogen bonding effects. When these tenets are observed, the partial fugacity of any component I in the bulk vapor phase is related to the mole fraction Xi of the guest species in the adsorbed phase by a relationship that is analogous to the Raoult's law for vapor-liquid equilibrium. P sub I superscript 0 is the sorption pressure. In the event that one or more of these tenets is violated, we need to modify this expression to include the activity coefficient for each of the guest species in the adsorbed phase. And when the activity coefficients are accounted for, we have the real adsorbed solution theory. The modeling of the activity coefficients could be done by invoking the Wilson model for the excess Gibbs free energy, the NRTL model, or the Margulis model. For further background, consult my paper in ACS Omega 2021. Watch also my presentation on the IAST for mixture adsorption equilibrium, the RAST for mixture adsorption equilibrium on my YouTube channel. When the tenets demanded by the IAST hold, we may derive a simple expression for the adsorption selectivity, which is the ratio of the component loadings, molar loadings for 1 and 2, divided by the partial fugacities of components 1 and 2 in the bulk vapor mixture. We may replace the ratio of the molar loadings by the ratio of the mole fraction in the adsorb phase. And in view of this expression, for the partial fugacities being proportional to the mole fraction in the adsorb phase via the sorption pressures, we find that the adsorption selectivity is the ratio of the sorption pressure of component 2 divided by the sorption pressure of component 1. The sorption pressures at thermodynamic equilibrium may be obtained by equating the integrals shown here for component 1 and for component 2 here. This is the surface potential phi, which serves as a proxy for the spreading pressure. The ratio of the adsorption pressures is uniquely related to the surface potential, and therefore the adsorption selectivity is a unique function of the surface potential for ideal mixture adsorption. CBMC simulations were carried out for 50-50 mixtures of CO2 methane in MFI zeolite that consists of a set of intersecting channels of 5.5 angstrom. The adsorption selectivity for 50-50 mixtures are plotted as a function of the surface potential phi and the mole fraction of CO2 in the bulk gas phase mixture. Additionally, we carried out CBMC simulations for ternary mixtures in the proportion 5, 15, 80 of CO2, methane and nitrogen. Another ternary mixture 20, 30 and 50 for CO2, methane and nitrogen. These simulations are shown by the green squares and yellow diamonds. The CO2 methane adsorption selectivity for the binary pair is not dependent on the presence or absence of the third species nitrogen, and the entire CBMC data set resides on a 3D surface mesh that shows that the CO2 methane adsorption selectivity is uniquely dependent on the surface potential and independent of the mole fraction in the bulk fluid phase mixture. This simple and important conclusion does not hold in the event that we have departures from the ideal adsorped solution theory due to violation of one or more tenets of the IAST. Let us examine variety of data sets determined from configurational-bias Monte Carlo simulations for a variety of guest-host combinations. I examine selectivity for mixtures of carbon dioxide and methane in Chabasite that consists of cages of 316 cubic angstrom. Each cage is separated from adjacent cages by narrow windows that have apertures of sizes 3.8 angstrom to 4.2 angstrom. The CO2 perches preferentially at the window regions, and therefore the mixture of CO2 and methane is not homogeneously distributed. This implies that the methane suffers less competition from CO2 than would be the case if the guest adsorbates were completely homogeneously distributed within the pore landscape. 4 different CBMC simulations were carried out. In 3 sets of simulations, the composition of the bulk gas phase mixture was held constant. The blue triangles are for 50-50 mixtures. The red circles are for 20-80 mixtures. The inverted pink triangles are for 1585 mixtures. The adsorption selectivity for each of these mixtures is plotted as a function of the total fugacity in the bulk gas phase expressed in pascals. We see that the 3 sets do not coincide because the compositions of the 3 mixtures is not the same. A 4th set of simulations were carried out in which the total fugacity was held constant at 1 megapascal, and the composition of the bulk gas phase mixture was varied from 0 to unity, and the adsorption selectivity is shown here to increase with the increased mole fraction of CO2 in the bulk gas phase mixture. These data imply that there are thermodynamic non-idealities that are in play, and we need to model the deviations from the ideal adsorption solution theory by introducing activity coefficients. As I have shown in my paper published in Fluid Phase Equilibria and referenced here, the deviations from ideality for CO2 methane mixture adsorption in Chabasite zeolite may be modeled using the Wilson model for activity coefficients, and the entire set of CBMC simulations for 4 different campaigns with varying surface potential and bulk gas phase compositions lie on a 3D surface that is shown by the blue colored mesh. The message to emerge is that the adsorption selectivity for a binary mixture in general depends both on the surface potential phi and the composition of the bulk fluid phase mixture. Thermodynamic non-idealities also prevail for CO2 methane mixture adsorption and DDR zeolite due to preferential location of CO2 in the window regions. CBMC simulations for 3 different campaigns were carried out to determine the adsorption selectivity of CO2 with respect to methane. The blue triangles are for 50-50 mixtures. The inverted pink triangles are for 20-80 mixtures, and the yellow diamonds are for mixtures in which the total fugacity in the bulk gas phase mixture is held constant at 1 megapascal, and the composition in the bulk gas phase mixture is varied from 0 to unity. The entire CBMC simulation data set resides on a 3D surface constructed using the Wilson model for the activity coefficients. This data shows that the CO2 methane adsorption selectivity is uniquely described by 2 parameters, phi, the surface potential, and the mole fraction of CO2 in the bulk gas phase mixture. For CO2 capture with NaX zeolite, we have deviations from the ideal adsorbed solution theory because carbon dioxide preferentially congregates on the extra framework sodium cations. And due to congregation around the cations, there is an inhomogeneous distribution of gas adsorbates, CO2 and propane in this case, within the pore landscape of NaX zeolite. The adsorption selectivity of CO2 with respect to propane is plotted as a function of the surface potential and mole fraction of CO2 in the bulk gas phase mixture. 5 different CBMC simulations were carried out, shown by the symbols here, and all 5 CBMC data sets resides on a 3D surface mesh that is created using the Wilson parameters for fitting of the activity coefficients describing deviations from thermodynamic non-idealities. We note that the adsorption selectivity varies smoothly, in other words, monotonically, with both surface potential and mole fraction of CO2 in the bulk gas phase mixture. We turn to adsorption of mixtures of CO2, propane in LTA4A zeolite. That's a cation exchange zeolite with 96 sodium cations per unit cell. These cations are located near the window regions, and CO2 also preferentially locates near the window region. This results in a inhomogeneous distribution of gas adsorbates because the propane molecules are located predominantly within the cages. 3 different CBMC simulations were carried out for determining the CO2 propane adsorption selectivity, and the 3 sets of CBMC data all lie on a 3D surface mesh that is created using the Wilson parameter for quantification of the activity coefficients in the adsorbed phase. The details of the IAST modeling is provided in my paper published in Fluid Phase Equilibria. We note that the adsorption selectivity varies smoothly with surface potential and the mole fraction of CO2 in the bulk gas phase mixture. And there is the behavior is seen to be monotonic. For adsorption of mixtures of water, ethanol, water, methanol, methanol, ethanol in microporous crystalline materials, we have the phenomena of molecular clustering due to formation of hydrogen bonding, and the ideal adsorbed solution theory will fail to provide a quantitative description of mixture adsorption equilibrium. I show here the configurational-bias Monte Carlo simulation data for 595 mixtures of water ethanol in chabazite zeolite. The green squares represent water ethanol mixtures in 50-50 proportions. The yellow diamonds are for water ethanol mixtures in which the total fugacity in the bulk fluid phase is held constant at 10 kilopascal. The excess Gibbs free energy is plotted as a function of surface potential and a mole fraction of water in the adsorbed phase. In this graph, the adsorption selectivity of water with respect to ethanol is plotted as a function of the surface potential and the mole fraction of water in the bulk fluid phase mixture. We see that the entire CBMC data set for the adsorption selectivity lies on a 3D surface mesh in which the activity coefficients have been fitted with the NRTL model to describe deviations from the ideal adsorbed solution theory. The variation of the adsorption selectivity is monotonic in both its dependence on the surface potential, phi, and the composition in the bulk gas phase mixture. A similar picture emerges for water methanol mixture adsorption in Chabasite zeolite. Three different CBMC simulations were carried out. 50-50 mixtures of water and methanol indicated by the red circles. The green squares are for 595 mixtures, and the yellow diamonds are for water methanol mixtures with a total fugacity of 10 kilopascal in the bulk gas phase mixture, and the composition Y1 is varied. The left graph is the excess Gibbs free energy plotted as a function of the surface potential and mole fraction in the adsorbed phase. The adsorption selectivity is shown here as a function of phi and the mole fraction in the bulk fluid phase. The variation of the adsorption selectivity is seen to depend on just two parameters, phi and the mole fraction in the adsorbed phase. The details of these calculations are provided in my paper in fluid phase equilibrium. Absorption of mixtures of methanol and ethanol in Chabasite also exhibit strong thermodynamic non-idealities, and the CBMC simulation data for 50-50 mixtures is indicated by the red circles, and the Gibbs free energy is plotted here as a function of surface potential and the mole fraction in the of methanol in the adsorbed phase. The excess Gibbs free energy is a function of both phi and x1. The adsorption selectivity of methanol with respect to ethanol is dependent on both phi and the composition in the bulk fluid phase. And you see that the CBMC data shows a smooth and monotonic dependence on these two parameters. Details in my paper cited here. For water ethanol mixture adsorption and DDR zeolite, again we have strong thermodynamic non-idealities, and the deviations from ideality is modeled using the NRTL description of activity coefficients as discussed in my paper, and the water ethanol absorption selectivity shows a unique dependence on the set of two parameters, phi and the mole fraction in the bulk fluid phase. We see that the CBMC data set resides on this 3D mesh that is created using the NRTL description of activity coefficients. The graphs here show the data determined from CBMC simulations for 50-50 water methanol mixtures in DDR zeolite, 595 water methanol mixtures in DDR zeolite, and the yellow diamonds are for mixtures in which the total fugacity in the bulk fluid phase is held constant at 10 kilopascal and the composition is varied. The excess Gibbs free energy is dependent on both the surface potential and the composition in the adsorbed phase. The water methanol absorption selectivity data determined from CBMC resides on a 3D surface mesh created from the NRTL model for quantifying the activity coefficients in the adsorbed phase. The adsorption selectivity is seen to vary smoothly and monotonically with both surface potential and water mole fraction in the bulk fluid phase. I show here CBMC data for 50-50 methanol-ethanol mixture absorption in DDR zeolite. The CBMC data are plotted by these red circles. This is the excess Gibbs free energy plotted as a function of the surface potential and methanol mole fraction in the adsorbed phase. The methanol-ethanol absorption selectivity is seen to depend on both the surface potential and methanol in the bulk gas phase mixture, and the 3D surface mesh has been created using the NRTL model for quantification of the activity coefficients in the solution. We again note that the absorption selectivity of methanol with respect to ethanol shows a smooth monotonic dependence on these two parameters. Indeed, for all the mixtures that have been considered in this presentation, many more mixtures are described and discussed in my fluid phase equilibrium paper. In all cases, the variation of the adsorption selectivity is seen to depend on these two parameters in a smooth and monotonic manner.